may work.
It may?
Yeah, just try.
Move
try
the
it.
computer now and change something.
Come on, like I told you, like on the from the top kind of thing.
Okay, let me try.
Just the left and the right. Yes, there you go.
Is it working when you don't do this?
No.
No, this doesn't.
On the top works. You see, with an angle, we managed to get away from the interference.
There is a spy in this room.
That's going to be interesting.
You're good?
I don't know.
Let's try.
I have no idea. At least it's not going to be my fault. So, hi, I'm Helger Lipmaa. I'm from University of Tartu in Estonia. And this talk is called Polymath, Groth16 is not the limit. The paper was at Groth24, so it's already a bit old. But also, to be honest, the results are back from 23, so it took a while to get it published. I think the first slide is very, I don't have to explain it here. We are working with ZK snarks. We have a prover and a verifier, and I think I nowadays take always this thinking point of view that zero knowledge is actually verifiable computation. So prover knows a computation, statement and the witness. The verifier knows computation and the public input X. And then you have a trusted third party who generates a structured reference string and sends it to both parties. And then the prover gives a proof that the computation is done correctly. So this known computation at known input and unknown W is, let's say, just equal to 1. And you have the usual requirements, completeness, soundness, or whatever, knowledge soundness, and zero knowledge. And obviously you want succinctness. Okay, so I think the kind of like one way of thinking like why I did what I did was that I was thinking about the landscape of snarks, and now there's a huge work on getting very prover efficient snarks. So there's like all kind of tensor code based stuff like breakdown, Binius. I think now the latest thing is Blaze. There's JKR with many versions, there's Fry with many optimizations, etc. And they're all good for prover. And then if you look at the other side, which snarks are actually good for verifier, the list is much smaller. So I think they are mostly, up to at least in 2024 summer, they were all pairing-based, Plonk was getting there, but mostly it was really like everybody who was interested in the prover efficiency was using Groth16. And then if you wanted to get something that was good for both, then there were all kind of like tools how to do it. One of them was snark composition. So you added, basically you composed a prover efficient snark with a verifier efficient snark. And when I looked at those papers, what they were doing was like JKR plus Groth16, breakdown plus Groth16, Fry plus Groth16, there was probably a few more. There was IPA base plus Groth16, etc. But it was always Groth16. Okay. Yeah, this is going to be interesting. Maybe I should stop doing it. So, and it's very kind of surprising because there's been a huge progress in the snark land, as you all know, during the last, I think now it's more than 5 years, like 6, 7 years. There's so many amazing constructions, but there's still this Groth16 that nobody has really been able to optimize. And it's still, at this moment when I was writing this paper, it had the shortest argument, it had the fastest verifier. So, and it was really like a dinosaur, like I'm not sure, is this T-Rex or somebody? So, 2016, some people here went to the grade school at this time. Not even grade school, like high school. So to give an intuition for those people who don't know what is a like SNARK composition, you basically have like your initial task. You have some computation that you want to prove. It's a huge computation. You have input and you have a huge witness. And then you give a proof that this computation is correctly done. You prove that x, w is in the original relation. And then the hope kind of like, here it's even good if this proof, like the output of the SNARK is maybe like square root of the input. Like you get like decent like downgrade, but you don't want to actually get something that is already constant size. And then the hope is that now you have a second SNARK that has like relatively okay prover, but doesn't have to be that fast prover because the input is like square root. But now you want this second SNARK to have very fast verifier. So, and the second SNARK basically proves that the verifier of the first SNARK accepted. So, because the input is long, then the first prover has to be very fast. The output of the first prover has to be short enough, but not like, you know, you don't have to like really put your, like, spend like 10 years with it. And you also additionally need to have verifier circuit has to be simple because you have to prove something about this circuit. And like already said, there's like quite a few candidates people are implementing, like the first circuit could be, first proof could be like something like breakdown or FRI or bulletproofs or like there's many candidates. I'm actually not an implementer, so I even don't know which one is the best right now. And then the second SNARK is that the input is going to be semi-long, so you need decent prover, but you really actually in many applications you would like to have like the as fast verifier as possible, as short proof as possible. And like I said, here people have been using Groth16 mostly. Then a few comments for those people who know Groth16. Groth16 is non-universal. The CRS depends on the computation. In this application, this is fine because the computation is that verify the computation of a given verifier of a known SNARK. So non-universalities, I would argue it's not an issue here. So one minus of Groth16 is already gone. Another thing is that Groth16, yeah, it has a relatively slow prover compared to all those fancy acronyms that I mentioned. But if the input is like like short, like square root or something like that, maybe that's not so important anymore. But then the question is like, oh, yeah, we have this Groth16, but can we actually do something better? Here, like a very short blurb of like how Polymath, like my new construction compares to Groth16. It's not a drop-in replacement. I personally think that actually this SNARK composition is maybe the most realistic application where you would like to use it. As a like standalone SNARK, it's maybe not so interesting. So if you compare it to Groth16, so Polymath has shorter argument. This is already yay because there was nothing shorter than Groth16 for like 8 years. And shorter, here you have to like compute, like what do you mean by shorter? So I'm computing the number of bits. So if you use the standard BLS12 381 curve, then in the 128, so it's like you get 128-bit security. There maybe this improvement is not so amazing, it's like 10%. But then like as time goes on, people find more attacks on elliptic curves. So actually people gradually, I don't know, slowly move to more secure elliptic curves. Like if you remember BN 254 was a really amazing curve, but it's kind of like, it's still like used, it's still in Ethereum, etc., but it's kind of like, it's less secure than it used to be. So if you want to move to 192-bit curves, then Polymath has already twice shorter proofs than Groth16. It also has faster verifier, although this is something that I would really like to see somebody who's a very, very good implementer to actually give me the numbers. I was doing all the mental arithmetic here, and I found out that if the input is short, then it's potentially faster, because instead of a pairing, I have a number of scalar multiplications. But then if the input is long, then it's definitely going to be faster, because in the case of Groth, you do basically scalar multiplication per every input element, and here you do field operations. So, but then again, I think a lot of people use like pre-hashing, so they actually use short input, so I'm not really sure. And another thing is that it's patch-friendly in the sense that there are no adversarially generated cheat2 elements, and this makes certain kinds of patching much, much better. So if you are into that kind of stuff, it's again like, it's much better than Groth16. And the bad things are that the prover is slower. Again, like I did mental arithmetic, I found out that it's like maybe 4 to 8 times slower than Groth16. So it's not maybe a very good standalone snark, but in the composition it should be fine. It uses random oracle. So that, given the discussion yesterday, this might be a problem, but I would say it's not very important maybe here, because I'm thinking about composition and the initial snarks, all those GKRs, etc., they use random oracle anyways, and I think the problem is more like with those snarks than with this Polymath. But one problem is that random oracle makes certain apps difficult, because Groth16 is malleable, and then you can do certain nice things like snarkback. This is not possible with Polymath. So, and like what snarkback allows to do is that you can collect pre-existing proofs from several sources, and then you can patch them. And this, at least, I don't know how to do. But if you, again, this is one concrete application where Groth16 is better. So I will go briefly through the process of Polymath. So the first thing is to remind what are pairings. Again, everybody here should know it. The only thing is that I'm a very strong proponent of additive notation, so I use additive notation absolutely everywhere, even in the target group. Although it's not important. I think in the next slides I don't use target group elements. So one in bracket sub 1 is element in group sub I is an element in GI, where the discrete logarithm is the stuff inside the brackets. And then we have bilinear map, and bilinear map basically gives bilinearity. What is maybe the important part in this slide is that if you are like a theoretical cryptographer, you don't think usually like how expensive is each group. But this is very relevant in practice. So you have to think that in the case of this BLS 12381, the field elements are like 256 bits, G1 is 384 bits, and G2 elements are twice longer. And if you go to 192-bit level, then the numbers blow up, and the number that really blows up is the last one. The G2 elements are 4 times longer. And then if you go to 256-bit world, then they are 8 times longer. So it's really like G2 elements are much more expensive, especially if you really care about the high level of security. So like one hint is that, what I'm doing, I'm trying to get rid of G2 elements. So very, very briefly now, so what Groth16, I'm not going to any details. What is happening is that the CRS depends on the computation, and then the proof is 3 group elements. 3 is good, but the middle one is in group 2, so it's actually twice longer than other elements, so you can think that it's actually like somehow 4 group elements. And verifier executes 3 pairings and the length of X group operations. So there's an optimality result. So Groth16 has 3 elements, and then also Groth proved that at least 2 group elements are needed, and one of them has to be in G2. So Groth16 has like 1 extra. And then there's a variant known that is using a different arithmetization where you can have 2 group elements. The idea is that instead of multiplication gates, you have square gates, and then the left and right inputs are the same, so you save kind of a 1 group element. The problem is that you have to use symmetric pairings, and symmetric pairings are very inefficient. So actually, if you don't care about the number of group elements, but the number of bits, this is going to be a much worse solution. But it's important to know that such a solution exists. So 3 group elements is definitely like not the minimum, but also if you think about this Groth's lower bound, first of all, it works in the standard model without random oracle, and the second thing is that it talks about the number of group elements, not about the bits. And if you maybe like mingle in group field elements, maybe you can like reduce the number of bits. And that was the very first thing that came into my mind, is that, oh, G2 elements are long, what can I do about it? I want to eliminate it. And then the kind of like hope is that you could, instead of B in group 2, you could have B in group 1, but the question is how. And then the basic idea is that Groth16 uses pairings for quadratic checks. And what I'm doing instead is that I'm thinking about it all as KZG commitments. I'm going to open the commitment as a field element, and then I'm using this field element to do quadratic checks. So that's very, very standard in like pairing-based snarks, like Plonk, etc. They do it always. And the nice thing is that KZG opening is shorter than a G2 element. So by opening, I mean a field element and a proof. Like field element and a G1 element, they are together shorter than a G2 element. So here is already a win. The problem is that it's still like this original B has to be also given as part of the argument. So it's still there. And in the 128-bit level, this is not a win. Interestingly enough, in the 192-bit level, this is already kind of enough because G2 elements are just 4 times longer. So in some sense, at that level, you could stop here. And then the next step is using this same square arithmetization where you have squares instead of multiplications. So in this case, B sub 1 is equal to A sub 1, so you don't have to transfer P sub 1, so you get 1 element less. The cost is that this makes prover roughly twice slower, because multiplication can be implemented by using 2 squarings and 1 or 2 additions, and this just blows up the circuit size. So this is, like I said, prover is 4 to 8 times slower. Factor 2 comes actually just from this, from using SAP as a different arithmetization. So multiplication gates go to squaring gates, circuit is going to be roughly twice longer. And then there's a number of very technical problems to solve. One of them is, this all sounds very nice, but if you actually know Groth16, Groth16 has 5 trapdoors, and KZG has only 1. KZG is a univariate polynomial commitment scheme. So the next question is, what can I do about it? And I'm basically reducing the number of trapdoors. So the first, univariatization from 5 trapdoors down to 1. And the idea is to replace each trapdoor with x to power of I, where x is a single trapdoor, and I is somehow well-chosen exponent that gives us efficiency and security at the same time. So this is something that I did in the BKC22 paper. I used exhaustive search for original Groth16 or a slight variant of Groth16 trying to replace the trapdoors with the powers of a single trapdoor. But the problem was that even after exhaustive search, the exponents are quite large. And like if you look at the KZG prover speed depends on the largest exponent that you can have. And you don't want to like multiply this with a factor of 20 or something. So I had to do something different. So the thing that I did was I basically used the same trick, but I first reduced the number of trapdoors. And then, because there's less trapdoors, there's a smaller system to solve to get security, and then I get smaller exponents. So first observation is that if you do Groth16 for SIP already, you have one less trapdoor, because there was like one trapdoor was related to the left inputs and another one to right inputs. So that gives me already like -1. And another observation is, well, it's not observation, it's novel work. So I noticed that the second trapdoor is needed in Groth16 to mask the CRS elements that only relate to the public input. So it's like, that's kind of like weird, like why do you need it? Because public input is so short. So here I optimized this away, and like I said, I'm using field operations here. And yeah, and an additional benefit here is that verifier becomes faster, because instead of the length of x group operations, it has to do length of x field operations. And then now we only have 3 trapdoors. We can basically, I applied exhaustive search to find out those powers of this single trapdoor that give a system where it still like has soundness or knowledge soundness, and so some elements cannot collide. But on the other hand, I want to have like as small exponents as possible so that the KZG prover would be efficient. And the exhaustive search gave me like concrete numbers, like one exponent is 3, another one is -5, but like the rest of the slowdown comes from this fact that those exponents are not 1 or 2, they are a bit larger. The problem is that if they are going to be like 1 or 2, then there are, in this knowledge soundness proof, there's going to be collisions between the powers of x that shouldn't collide, and then the soundness goes away. And then there's another trick, so I don't, like this is very short, so it's, the problem is that to do all this stuff, I have to use like this Groth16 setting that you have a circuit-dependent SRS, but this SRS has holes. You cannot use this SRS to compute KZG proof. So I just added more elements to the SRS that depend on a new trapdoor. There might be a more clever way of doing it, but it just worked. It almost had added no like costs. And that is the kind of idea like behind Polymath. Like I already talked about the efficiency. I'm not going to give concrete numbers. They are all in the paper. I think for real efficiency, you really need an implementation. I know that there is an implementation around, but I was just recently informed by a third party that this implementation is not good. So like it's extremely unoptimized. And the very final thing that I want to mention is security proofs. One thing is that completeness and zero-knowledge proofs are short and standard. There's no problem there. Soundness proof itself is 7 pages. Like if you know Groth16, the soundness proof is very long. And now, because of those colliding powers of x, etc., it gets even worse. And then I also tried to get like a bit better security. So to get tight security after Fiat Shamir, I proved special soundness. That added like half a page at least. And finally, the proof is given in the AGM with oblivious sampling. Like if you, in the TCC paper in 2023, we noted that KZG is often used strongly. Like if you look at some of the existing proofs, they the proofs don't work if adversary can obliviously sample group elements. So I try to basically iron tight my proof as much as possible, but it's complicated. And yeah, I think that's it. It's first improvement on Groth16 since 2016. I wrote that hopefully encourages other researchers to improve Groth16 even further. I know that now there are other works. I think Pari is going to be presented soon here. And then I also saw some recent e-prints saying that if you just want to do designated verifier, then you can even just do one group element. So people are now finally working on it. And yeah, open problems, the prover speed is not so good, but I think in this application it's okay. And I think the theoretical question is that now we have random oracle, does Groth's lower bound actually hold? What is the shortest that we can get? I have no idea. And that's it. Thank you.
Thank you. We have a question here.
So you use the square arithmetic program.
Yes.
What about using exactly the same approach, all the optimizations you've done, everything, but without the square? Like, of course, like the proof size would grow, but the prover would be more efficient, and maybe at some security level you would also get something.
Yeah, I shortly mentioned it. I didn't work out the details, but the kind of idea is that if you like the reason to use the square is that you get down, like you win one group element. And this is what allows Polymath to be like have a shorter proof than Groth16 even in 128-bit level. But in 192-bit level, this is actually not needed. So yes, I think you can basically you get twice better prover when you just use the R1CS. So that's the trade-off.
Any further questions?
Hey, so why do you need to do the univariatization? I mean, if you're going to need a special SRS anyway, because you need the holes, would you lose something by just staying with something closer to Groth16 with all the 5 trapdoors, or however much it is? Wouldn't be a little more prover efficient because the powers don't go higher? Or?
That's a good question. I don't know how to do it. Like, because like if at least the obvious multivariate extensions of KZG have worse proof size.
Oh, you're saying the thing you need to open, if you stay with the original trapdoors, it's not just in powers of X. It's
so there's going to be KZG opening. I'm using standard KZG there, so the opening is one field element, proof is one group element. I don't know, maybe there's a clever way of somehow doing it differently, but all the multivariate and even bivariate variants of KZG have a much longer proof size.
We have a question. What time for one small question, more question? All right. Let's thank the speaker again. Thank you, Helger. And we're going to set up. Just a small reminder that after this talk, we finish the morning session, and then we have a break with some coffee and treats.